All right, thank you for the invitation to speak. I've been asked to give a talk on the application of effective field theory methods in gravity. This is a topic that has considerable overlap with talks we've heard this morning and some talks we've heard in the previous days. So to get started, it's been known for a long time now that on the basis of general principles like Lorentz invariance and unitarity and so on, even though we don't know quantum gravity in the ultraviolet, we know that in the infrared, the interactions of gravitons are described by the Einstein-Hilbert Lagrangian. Meaning that you can take this Lagrangian, quantize it around the fixed background, like let's say flat spacetime, expand out in powers of the graviton field, read off Feynman rules, and calculate observables. And of course, if you do this, you get a huge number of, infinite number of self-interactions from expanding root GR. So the fact that there's a huge number of interactions leads to an arbitrarily high dimension, leads to UV problems, which in modern terms we understand to mean that this theory is just a low energy effective field theory, which has limited predictive power, but nevertheless it can make definite predictions. And so here I just list a couple. For instance, one of the first calculations by DeWitt of graviton scattering, and it gives a well-defined and actually quite simple result. And of course, it's ridiculously small phenomenologically, so it's not something that anybody is going to see anytime soon. And another example are the quantum corrections to the Newtonian potential, as emphasized by Donahue back in the 90s. Again, this is a quantity that's calculable in this effective field theory up to contact terms that are not accessible. But at long distances, there's a well-defined correction. There's a well-defined effect with a calculable coefficient. As we heard this morning, doing computations in this theory of interacting gravitons as well as supersymmetric generalizations, there's been huge progress in that with new ideas. And so this huge progress has been going on for the last decade or so. And the new ideas were mentioned this morning, things like the double copy or generalized unitarity and so on. Maybe less academically, this effective theory also calculates things of, and more recently, this effective theory also calculates things that are relevant phenomenologically. For instance, observables in the early universe, where now the suppression scale, or the suppression is not it's not as suppressed because the Hubble scale is large. So these sort of calculations, for instance, in early universe cosmology, are part of what one could call sort of a modern, the modern effective field theories of gravity, which are interacting field theories of gravitons coupled to matter. They have applications to astrophysics and cosmology, and typically these effective field theories have some elements that are maybe not familiar to people who do effective field theory, say for collider physics. For instance, you may not have full Poincare invariance, or you may be in an initial state which is not the vacuum, it's not trivial, or there could be non-trivial sources, strings, branes, defects of some kind, and there could also be special kinematics. So so anyway, so that's sort of the setting. And like in ordinary effective field theories that we're used to, these theories, effective theories of gravity, exhibit decoupling of short distance degrees of freedom, allow for a separation of scales systematically as a power counting in a small parameter, which is the ratio of the scales. And constructing these effective field theories allows you to use the renormalization group to sum logs in the usual way. However, even though the usual ideas are there, there are also perhaps theoretically novel elements that are not always seen in effective field theories of high energy physics. For instance, the boundary conditions for the path integral in some cases are Schwinger-Keldysh type initial conditions rather than Feynman boundary conditions, such as in amplitudes. The effective Lagrangians in these theories can have couplings which depend on space-time coordinates, running couplings or counter terms that depend on space-time coordinates. And then there's also time dependence in the renormalization group in some sense. And finally, I guess the perhaps the most subtle issue facing effective field theory in gravity is the presence of horizons. And so in recent years, there's many examples of these sort of effective field theories that I outlined here sort of generally. So there's effective field theories for inflation, for large-scale structure, effective field theories for understanding infrared physics in de Sitter space. There's even soft collinear effective theory of gravity, and so on. These examples all exhibit the kind of general features that I mentioned in the previous slide. But the one that I'm most familiar with and I want to describe now in some detail is an effective field theory for compact binary systems as an effective field theory of gravity. So the effective theory that I'm going to describe with however much time I have left is an effective field theory that describes the dynamics of binary neutron stars for black holes. For the sake of this talk, I'll just call them black holes and think about black holes. And so if you have two of these objects, which these systems are relevant for LIGO physics, that was discussed this morning. And in the non-relativistic stages, early stages of the evolution, this is a system which is sort of a perfect system for effective field theory because it involves a hierarchy of scales, ranging from the size of the objects, for instance, for black holes, the horizon size, to the orbital radius, to the wavelength of the radiation. And furthermore, these scales are all correlated in the sense that they involve ratios of velocity. So the goal is to calculate systematically as an expansion in velocity, but the physics at all these different length scales shows up. And so the way that we dealt with that is by constructing, actually it's two effective field theories, and they appear sequentially, starting with what we're trying to describe, which is general relativity, let's say in vacuum for black holes, so a system of two black holes interacting. And so what we do is we integrate out a scale at a time. So first we integrate out the size of the objects to construct a effective theory of defects of world lines with localized degrees of freedom that couple to gravity, and which describes finite size effects, for instance, perturbations of the horizon, quasi-normal modes, and so on. If you keep zooming out, if you keep scaling, you eventually reach a point where the separation between the two objects is relevant. The two objects are point-like and non-relativistic, and then we can describe that system as a theory of potentials and radiation that you obtain by matching from the UV. Finally, there's another theory at the very end of this thing, at the very longest wavelengths, which is a theory of radiating multiples. It's actually the same effective field theory, roughly speaking, as what you get to describe the finite size effects. So with my remaining time, I'm going to say a bit more about what these theories are and what you can calculate with them. So let me first describe the theory that describes both the UV and the IR of the system, which is a theory of dynamical multiples coupled to gravity. So this is a world line with a bunch of degrees of freedom to live on it, coupled to the curvature. So here you see E and B. Those are the various components of the Riemann tensor. I'm not going to bother defining them. as well as systematic gradients of them. And the coefficients depend on time. These are, in a sense, Wilson coefficients, which are time dependent and are determined by matching to the ultraviolet. So for example, if you have 2 point objects orbiting each other in a non-relativistic system, matching just means the multiple expansion. But in gravity, the multiple expansion is more complicated than what's in Jackson's textbook because of nonlinearities. And so to match, you just calculate the amplitude to emit gravitons from this 2-body system of world lines, take a long wavelength limit, and you immediately can read off the multiples from that. And so here I've shown you how that works at the next to leading order. So a leading order, you just get the usual moment of inertia tensor, and then you get gravitational corrections to that from higher order diagrams. Once you know the moments, or even if you don't, you can then use the IR theory to calculate radiated corrections. So these are amplitudes for these moments to emit. These moments are sources, and they emit radiation out to infinity. And so again, the nonlinearities in gravity make this complicated and also interesting because there's both infrared and UV effects, which I obviously have no time to describe. I'll just say something about the UV. So the IR, the resolution is that when you calculate physical things, the infrared physics is well behaved. The infrared divergences cancel. As for the UV, well, that's just renormalization of the moments, of the Wilson coefficients in the theory. So here's the leading order renormalization group equation for the quadrupole moments. And the utility of this is that it allows you to resum logarithms of the ratio of the scales, namely the velocity, that appear in observables. And so here I'm illustrating this with a calculation of all the logarithms, quadrupole logarithms that show up in the radiated power from a circular orbit. So 2 black holes in a circular orbit in units of the leading order quadrupole formula. This is not the exact answer. This is just the series of logarithms. And so the renormalization group allows you to very simply predict the whole pattern of logarithms. This is something that we worked out about a decade ago and recently has been extended to the renormalization of all moments. The final thing I'll discuss is matching the UV theory of the composite object. So this is a theory of dynamical moments that now describes the internal dynamics, let's say, of the black hole. The way that we match this theory to general relativity is we consider a isolated black hole, and then we look at processes with gravitons being either emitted or absorbed by this object, and then compare to the full theory predictions. So for instance, you can read off the positive frequency part of the correlator of these moments by calculating the absorption cross-section and matching to an old result of Page. Or if you wanted to, this is not relevant for phenomenology, obviously, but if you wanted to, you could also incorporate quantum effects. So if you look at emission, you can also match that by comparing to the Hawking emission rate. And then the point of that is that once you've done the matching on shell, effective field theory predicts that the same processes, the same correlators will show up when you do off-shell graviton exchange. And so doing that allows you to calculate from this simple matching calculation, non-trivial binary dynamics. And so just to give you an illustration, here's recent results by Jimping Li, Ira, Rothstein, and myself from last year. These are phenomenologically relevant results for the orbital evolution of, in this formula, I've taken the near extremal Kerr limit. So these are 2 spinning black holes. And so there are frictional forces having to do with the presence of the horizons, and they're calculable in this theory. So this is a instantaneous quantity. It's valid for all times. It's not some average. You can evolve this in time. And so here are the frictional forces on the two objects, the precession, the torques on the black holes due to the fact that the horizon has a finite size. And finally, what people in this subject call the Horizon Flux, which is the amount of energy being dumped into the horizon. This is actually a phenomenologically relevant result that comes in at relatively lower in the velocity expansion. And you'll notice that dE dt can have either sign, positive or negative. Positive corresponds to dissipation, absorption by the horizon. This quantity can also be negative because of the Penrose process, or similarly superradiance, which allows you to extract energy from the rotating black hole. In fact, that's why this is so enhanced. And so here's the result. For arbitrary initial data, you can evolve this equation. You can also do less phenomenological things with this theory that are nevertheless of theoretical interest. And so one example that I have here is what we believe to be a new phenomenon in perturbative quantum gravity, having to do with off-shell exchange of Hawking radiation between, let's say, a black hole and an elementary particle. So this is a calculation that is well defined in the effective theory and tractable once you've done the matching. And so here's what it looks like. The point is not so much that the result, but that you can do it. And what is interesting about it, at least to us, is that it's in the power counting, it comes in at an order comparable to the calculable corrections from canonical quantum gravity that was studied back in the 60s and 70s and all the way up to modern times. So that's all I have to say. I'm probably not doing great with time in any case. I'll just conclude by saying that effective field theory ideas play an important role in gravity, or are quite useful to gravity, not just theoretically, meaning that there's new ideas in effective field theory, new types of effective field theory, new applications of the renormalization group, and so on. So it's not only theoretically interesting, but also phenomenologically relevant. And so I gave you some examples of that. So I'll end there, and I'm happy to answer any questions. Thank you.
Questions? Comments?
Is this thing on? Okay, no comments.
Hey, Walter, this is Lance Dixon. Thanks for a nice talk.
Hey, Lance.
Can you go back to that slide about resumming logs?
Yeah.
Because those logs have very large powers of the small parameter in front of them.
Precisely, yeah. So
yeah, so maybe you can comment on their impact and stuff.
Let me find it.
Yeah,
you're right. So that's why I put resum in quotes, because they're never large because they have these powers of velocity in front. So you can actually see from the RG equation itself on top that the right-hand side is suppressed at small velocities, because gm omega goes like v cubed. So this is actually summing, at least in the quadrupole channel, or telling you about logarithms involving powers of v to the 6 log v. So it's not systematic. I'm not claiming that this improves any approximation. The only point I wanted to make was that the pattern is completely fixed by the renormalization group. And we actually, these coefficients, we actually obtained them in effective field theory. And they also show up in other limits. For instance, when people calculate what's called black hole perturbation theory, where you're doing a point particle orbiting the actual Kerr black hole. So you have the full gravitational field of that black hole. And so those logs show up there, and so it's a cross check.
That's a self-force region?
Yeah, I think it's called self-force or black hole perturbation theory.
Okay, that's interesting that you can.
So that's the only point I wanted to make. I didn't want to imply anything stronger about this quote unquote resummation.
Thanks.
Sure.
Any other quick question? Anything online?
Not online, but if I can abuse my microphone privileges again. Hi, Walter, this is Nathaniel Craig. Thanks again for
Hey.
If I can ask, maybe it's a naive question. I think it's on your last slide. Is there an easy way to understand why the virtual Hawking radiation exchange contribution shows up at the same order as the normal sort of one loop vacuum polarization?
Yeah, so easy. I'm not sure I have a intuitive explanation of it that I can just say in a few lines. It actually confused us for a long time whether the effects of Hawking. So at first we were getting results that the Hawking radiation was not Planck suppressed, and it turned out that it was because we were matching incorrectly. And so it's kind of interesting that at the level of the actual correlators, the quantum and the classical effects come in at similar orders, but at the level of the observables, there are cancellations. And so when you include the effects of Hawking radiation, you can prove that they never come in classically. They come in only Planck suppressed. So it's not a real answer to your question, but sort of the best I can do. Maybe Ira can explain it. I think he's there. So.
All right, I'll corner him later. Thank you.
Thank you.
Yeah.
Let's thank Walter again.
Okay, thank you.